Hi everyone, and welcome back to my channel in Economist. So, if you are following my Econometrics playlist, you will know in the previous video I have explained what is heteroscedasticity. So, if you haven't watched that video, please check that out because this video is going to be a continuation of that particular video only. So, you have to watch that video before in order to understand this video. So, in this session, what we are going to do, I will be explaining to you a very important question that by WLSE, that is the weighted least square estimator, is blue estimator under heteroscedasticity. So in the previous video, I have talked about that by OLS is not a good estimator if heteroscedasticity is present. Now, in this video, I'll be explaining to you if heteroscedasticity is present in your model, how do you convert that model into a homoscedastic model first, and then using that homoscedastic model, how do you prove that WLSE is a better approach, than OLS and all the other method of estimation if heteroscedasticity is present in your model. So let's start with that. How do you prove that WLSE is blue under heteroscedasticity? As always, we start with a two variable regression model which looks like this. Yi is alpha plus beta xi plus epsilon i. This is our simple two variable regression model. Now, what we have to do, we will assume that sigma I squared, this error variance is heteroscedastic. This is the error variance. Not only that, we will assume a functional form for this particular heteroscedastic error term, right? This is the term for all I. Now, what does this term mean? This means where the zi's are some known values. Zi's are some known values, that is, we know the error variance, up to a multiplicative constant, right? So what we have assumed so far is that we have started with a regression model, two variable simple regression model. We have assumed that heteroscedasticity is present in the model, that is the error variance depends on the xi values basically. Not only that, we have assumed a functional form for this error variance, heteroscedastic error variance, which is sigma square, which is constant, into zi square, which means as you vary the value of zi's, this sigma i's will vary. That is, we know this error variance up to a multiplicative constant. So this sigma square, this much we know this much, but the additional variance that will be added, that will be varied with the value of zi. So this is the structure of the model now. Now, the question is, how do you convert this heteroscedastic model into a homoscedastic model? Because as we know that if heteroscedasticity is present, I have explained the consequences also in the previous video, that if heteroscedasticity is present, how will the result will give you misleading results basically. OLS will give you misleading results. So it is very necessary for you to convert this heteroscedastic model into an homoscedastic model. Now, how do you do that? For that, you have to use a method. You will consider sigma epsilon I upon. Now see, the process is whatever term you have here, take the square root of that, whatever term you have. So the square root of zi square is zi. Suppose here instead of zi square, you have only zi. So here in the denominator, you will have root zi then, right? Whatever term you have here, just take the square root of that and that will come here. Now, if you write variance in this fashion, what will this be? Zi's are known values, these are constant. So zi square will come out and it will be simply variance of epsilon I. Variance of epsilon I. Now, variance of epsilon I is what? This is sigma I square upon zi square. Now, what is sigma I square? As I have written here, this is sigma square into zi square upon zi square, which is simply sigma square, which is a constant. So what we see here is that if you divide If you divide epsilon I by zi, then the error variance will become constant. Hence, variance of epsilon I upon zi is a constant term, is a constant for all I. So what does this tells you? This tells you that so we can transform. This will give you a hint that we can transform our original model, as follows. So what will be our modified model? Our model, initially it was this alpha plus beta xi plus epsilon I. Now what do you have to do? You have to simply divide every term by zi. Simply divide each and every term by zi. Why I have done that? Because this is the hint. This will give you the hint that if you divide epsilon I by zi, then you are getting a constant variance, right? So dividing the model, dividing every term with zi will give you a homoscedastic model, and that is our aim. That we want to convert our heteroscedastic model into a homoscedastic model, and that is why you have to use this transformation. This is called the transformed model, basically. This is the transformed model, and the special feature of this model is that this model is homoscedastic. This model is homoscedastic, right? Because the error variance is constant. Basically, here this is the error variance. This is the error variance, and we have just showed that this error variance is constant, right? So this is the method. If heteroscedasticity is present in your model, you have to convert this into homoscedasticity. Now, what you can do, you can consider this entire term to be some yi prime. This entire term to be some alpha prime, plus this term you consider it to be beta xi prime, and this term you can consider it to be epsilon I prime. So this will be our transformed model, the reduced version of our transformed model, right? So you can write since each observations xi yi is assigned a weight. What is the weight? Weight is simply 1 by zi here. If you see here, xi is given a weight of 1 by zi, epsilon I is given a weight of 1 by zi, and alpha is also given a weight of 1 by zi. If this is the case, assign the weight, and this method is called weighted least square. Weighted least squares, or WLS, right? This method is called the weighted least square method or WLS method. Now, what we will do next is that we will use this transformed model. To show that WLSE estimator. So the estimate that you find from this model, basically this beta cap or beta coil that you will find out from this model will be the blue estimator of beta, and that is why that is the proof that we are going to do now. Let's see how to show this. Now in this model, you can include this intercept, or you can do this without the intercept. Let me do it without the intercept, and you can try the intercept version on your own. Suppose beta curl is the WLSE, weighted least square estimator of beta. So we start with this assumption. Now what we do, then we need to minimize the error sum of square which is epsilon I prime cap square, right? If you do that, the structure of the beta curve will remain the same. There will be no change in the structure, only the values will be weighted now. Summation I from 1 to n. This will be xi prime, yi prime upon summation I from 1 to n, xi prime square. This is what will happen. Now you can replace the values of xi prime and yi prime. So it will be summation I from 1 to n. Xi prime is nothing but xi upon zi. Yi prime is yi upon zi. And summation I from 1 to n, xi upon zi whole square. This is what will happen. Now you can again substitute this yi upon zi value here. See, from our transform model, yi upon zi is alpha upon zi, or we are not taking this intercept term in our model right now. But you can include this, the results will be absolutely the same. So this portion, only this portion we will include. So it will be summation I from 1 to n, xi upon zi, and here you have beta xi upon zi plus epsilon I upon zi, and the denominator is the same. I'm not writing it, denominator will be the same. This particular term is the same. Now if you see, if you multiply this, the first term, then it will be beta summation xi upon zi whole square, which is the same as the denominator. So this term will cancel out. Let me do it in the next page. So beta curl will come out to be, okay, let me write another step for you. Summation. So beta will come out I from 1 to n, xi upon zi whole square. And then what do you have? Summation I from 1 to n, xi upon zi, and then you have epsilon I upon zi, right? So the denominator remains the same, which is xi upon zi whole square. Now if you individually apply the denominator, it will be beta plus this will be as it is 1 by n xi upon zi epsilon I upon zi summation I from 1 to n xi upon zi whole square, right? Okay. Now if you apply expectation on both sides, this will be beta only, and here you see the expectation will be on this particular term or this entire term. You can consider this entire term because xi and zi both are known values, non-stochastic known values. So expectation will not be on this or on this. So you can write summation I from 1 to n xi upon zi into expectation of epsilon I upon zi upon the denominator. Now expectation of epsilon I is simply 0. Expectation is not changing. If this is 0, the entire term is 0 basically. So this will give you expectation of beta curl is simply beta. Now what does this tells you? This tells you that, let me write it here, the WLSE estimator, is still an unbiased estimator. Unbiased estimator. If you are following my channel, you will know that this is the unbiasedness property. I have covered this multiple times, that if the expected value of the estimator is actually equals to the true population value, then this estimator will be an unbiased estimator. And this property is holding for WLSE estimator as well. So in heteroscedasticity, OLS estimators are also unbiased and WLSE estimators are also unbiased, right? Now the difference will come in terms of the variance. So let us compute the variance and then compare the variance of what we have got in OLS estimator and now what we will be getting in WLSE estimator, and then we will compare and come to some results. So let's see, how do you find out the variance of this WLSE? Simply expectation of beta curl minus beta whole square, which is expectation of See, beta curl minus beta will come from this portion. Beta curl minus beta. If you take this beta on the left hand side, you will get this remaining part. So let me write summation I from 1 to n xi upon zi epsilon I upon zi. Then in the denominator you have summation I from 1 to n xi upon zi whole square and a whole square of this entire thing. Now whatever terms are constant, that will come out. Xi and zi, whatever terms you have in terms of xi, zi, that will come out. And this will give you 1 upon summation I from 1 to n xi upon zi whole square of that, and then expectation of summation I from 1 to n xi upon zi epsilon I upon zi and a whole square. So now you can take the square individually. Here you see, here you have this into this and whole square of that. So you can apply this whole square inside. So let me take this square inside. So here you will have square, here you will have square. Now this is same, I from 1 to n xi zi whole square and a whole square of that. And then this in this particular portion, summation I from 1 to n xi upon zi square will come out because they are constants basically, and expectation will be on this particular term. Epsilon I upon zi whole square. Now what will be this particular expression? This will be simply sigma square, right? Epsilon I zi. And if you compute the expectation, this will be simply sigma square. Let me show you here. Expectation of epsilon I upon zi whole square. So it will be 1 upon zi square into expectation of epsilon I square. So this will be sigma square, zi square upon zi square. So this cancel out. So it will be only sigma square. And that is what I have written here. This will be only sigma square. Let us go to the next page. So altogether, what will be the answer for variance of beta curl? If you see from here, this portion will remain. Here you see one square will cancel out. One square will cancel out. Here you have sigma square. So it will be sigma square upon summation I from 1 to n xi upon zi whole square. So this will be the variance. This is the variance of WLSE estimator. Now in the previous video, I have derived for you the variance of the OLS estimator. Do you remember this? If you don't remember, you can check the process. I have derived the entire thing. I'll give the link in the description, and also I'll add that video in the iCard. So check that out. Summation I from 1 to n xi square sigma square. So let me write zi square, and then sigma square will come out. Here you will have a sigma square. So this is what we had derived in case of homoscedastic variance, variance of OLS estimator, basically. Variance of OLS estimator. Now what you have to do, you have to simply compare these two variances. Compare these two variances and see which one is the lower variance, which one is the minimum variance. Whichever is lower, that will be a better estimator. If this is lower, then WLSE will be a better estimator. If this is lower, then OLS will be a better estimator. Now for that, how do you do? Simply divide. Simply divide. If you divide, what will you get? Sigma square summation I from 1 to n xi upon zi whole square summation I from 1 to n xi square whole square upon sigma square summation I from 1 to n xi square zi square. This is what you will get. Now the sigma squares will cancel out. Now the remaining portion. How do you find out the relationship in the remaining portion? For that, what do you have to do? You have to use the Cauchy-Schwarz inequality. Cauchy-Schwarz. Right? I hope you have heard this name. What is Cauchy-Schwarz inequality? It says this: summation ui square, summation vi square. This will be simply greater equals to summation ui vi and a whole square of that. So this is simply the Cauchy-Schwarz inequality. Now you have to use this inequality in our particular case, that is in this particular case. Now the question is, how do you define ui and vi in our particular case? You can pause the video and think for yourself and then see the solution. What you have to do here, ui will be simply xi into zi and zi will be simply xi upon zi for all I. For all I. If you do this and then apply this Cauchy-Schwarz inequality, see what happens. This will be summation I from 1 to n. ui square will be xi zi whole square. Xi zi whole square basically. And then you have summation vi square. That will be summation I from 1 to n xi upon zi whole square. And that will be greater equals to summation I from 1 to n xi zi into xi upon zi and a whole square of that. So zi will go out and you will have, this is as it is. Xi upon zi whole square. No change in this term, and this will be simply summation I from 1 to n. See, here it will be xi square whole square. Xi square and a whole square of this. Now you can divide I from 1 to n xi zi square summation I from 1 to n xi zi whole square upon this term comes here, summation I from 1 to n xi square whole square. And this will be greater than equals to 1. Now, can you identify what is this term? Let's go back and see. This is exactly this particular term. This is exactly this particular term. You can pause the video and take a screenshot and do it for yourself. You will see only this ratio will come in the reverse order. So it is simply, let me write it in the next page. So this is simply variance of beta cap. Beta cap is OLS basically, variance of the OLS estimator. And this will be the reverse of this basically. This is exactly the reverse of this. See, this summation I from 1 to n xi square whole square, this term comes in the denominator and the rest of the things are in the numerator, right? So this is exactly this particular thing. So this is greater equals to 1, which basically tells you variance of the OLS estimator is strictly greater or equals to variance of the WLSE estimator, right? So what we can say, beta curl is the is the blue of beta. And what we will conclude? We will conclude that WLSE has the least variance. WLSE has the least variance, and hence it is the blue estimator. And OLS is not a blue estimator. So under heteroscedasticity, what we have proved is that OLS is not the blue estimator and it is always advisable to use WLSE estimator. So unless heteroscedasticity is present, the estimators are still remain unbiased in case of either in case of OLS or in case of WLSE, but the difference will come only in case of the variance. And we have proved in details that the variance of the WLSE estimator will be strictly less than or equals to variance of the OLS estimator. And I hope this video is helpful to you. Let me give you a quick recap of what we have done. In the next session, we'll be starting with the goal-filled quant test, right, of detecting heteroscedasticity, and we'll solve some questions on that. So we started with a model, with a regression model, which has heteroscedasticity present in it. So we assume that heteroscedasticity is known to us only up to a multiplicative constant. Now this functional form might change. This can be sigma square zi cube. This could be zi only zi. This could be zi to the power 4 or anything. This could be any form. I have taken the simplest form. So what you have to do to convert the model, any functional form they give you, you only have to square root this particular thing, and this will be converted into a homoscedastic model. Now this homoscedastic model, since it has weight associated with each of the term, weight is 1 by zi in our case. So this model is called the weighted least square, WLS model, or the weighted least square model. Here I have written this is the weight, 1 by zi is the weight, this is the weighted least square model. Now if you find out the estimator of this model, this will give you the weighted least square estimator basically. And we have assumed beta curl is that weighted least square estimator of beta. Then in details, we have shown that this estimator will be unbiased since expected value of beta curl is simply equals to the population parameter. So it is unbiased. And then I have shown you how to find out the variance of this estimator and why this estimator is the blue estimator, because it captures the least variance. How do you find out the least variance? We have to take the help of the Cauchy-Schwarz inequality, which is something like this. This is Cauchy-Schwarz inequality. Now assume this ui vi appropriately and use this inequality, and this will give you this result. I hope you find this video helpful. If you do, please like and subscribe to my channel AN Economist. If you find any value with this video solutions, I hope you are getting values from this. If you do, please subscribe to this channel. It gives me immense motivation to continue making these videos. And let's meet you in the next video. That will be part 3 of heteroscedasticity, and I'll be going into goal-filled quant test. And thank you for your time.